Hi everyone. Well, our next topic when we're talking about complex numbers is how you multiply complex numbers. First thing we need to talk about is that multiplying complex numbers is really no different than multiplying algebraic expressions that have variables in them. And we treat the I, as we mentioned before, pretty much like a variable. There is one small thing we need to look out for, however, when we're doing these multiplications with complex numbers. And that is what happens when you have an I squared. Let's take a look at that first. We talked about the fact that by definition, I squared is -1. Okay, we said that was the definition, but we also said that when we multiply I times I, and if I is the square root of -1, we know that when we multiply a square root by itself, all it does is get rid of the square root sign, -1. Okay, so what does that mean in terms of our problems? Well, if I end up with something, say, that says 5i squared in a problem, that is 5 times, and we just said I squared is -1. So 5i squared is actually -5. And I can do that the same with any other number. What if I had 20i squared? 20i squared is 20 times -1 or -20. If the number were negative in the front, say -3i squared, that would be -3 times -1 or +3. So I hope you can see that there is a shortcut, if you want to call it a shortcut to these, and that is if you have a number with an I squared attached, all you really need to do is get rid of the I squared and change the sign. So if I had, for example, 12i squared, get rid of the I squared and change the sign. It's that simple. If I had -7i squared, get rid of the I squared, change the sign to a positive. That's the only additional piece of information you need when you start multiplying complex numbers, other than treating the I as if it were a regular variable. So let's see what happens when we start doing some problems. What if I had -6i times 3i? Just a simple multiplication. Well, I think you know that if I had had -6x times 3x, you folks would have no trouble telling me that the answer to that is -18x squared. -6 times -6 times 3 is -18. X times x is x squared. No difference here. -6 times 3 is -18, and I times I is I squared. But we just talked about something up here, and that is anytime we have an I squared attached to a number, all we do is we get rid of the I squared and change the sign. So that -18 becomes a +18. So again, -6i times 3i gives us 18. Another situation where two imaginary numbers multiplied together give you a real number. Unusual, but it happens. Let's look at another example. How about -4i times -7 plus 7i? Now, if I had written this problem, -4x times -7 plus 7x, I would hope that you would have told me, well, all you got to do is distribute this. And you'd say, sure, that's how you do it. So that's what we're going to do here. Let's distribute. -4i times 7, -4 times -7 is 28i. And then -4i times 7i is -28, -4 times 7. I times I is I squared. The difference here is we're not quite done. We have 28i, and again we have our I squared situation here. What do? We get rid of the I squared and change the sign on the number. We're going to make it a +28 instead, because multiplying by I squared is the same thing as multiplying by -1. And then our last step is to make sure we write this in standard form. The real number has to come first. So your final answer is 28 plus 28i. Not too bad, is it? Now let's take a look at one more example, and that one more example is going to be a foiling problem. 2 plus 3i times 6 plus 7i. When we have two terms in each parentheses, I think you know that you're supposed to FOIL these. Okay? It's just a double distribution here. So we're going to do 2 times 6 is 12. 2 times 7i would be 14i. On the inside, we have 3i times 6. That's 18i. And then 3i times 7i would be 21i squared, wouldn't it? And then our last bit of business here is to combine some like terms. How about 14i plus 18i? Wouldn't that be 32i? Sure would. Plus 21i squared. There it is again. So what do we need to do? Let's rewrite this. 21i squared, take off the I squared, change the sign. So that actually gives us a negative 21, which creates two more like terms to combine. 12 minus 21 is negative 9 plus 32i. There's our answer. Make sure it's in standard form. Don't write 32i minus 9, mathematically equivalent, but not in the right form. I do want to point out one other thing to you, and that is, what if I had 4 plus 2i times 4 minus 2i? Let's FOIL that. 4 times 4 is 16. My outside terms, 4 times negative 2i is negative 8i. Inside, 2i times 4 is positive 8i. And my last terms, 2i times negative 2i is negative 4i squared. I hope you can see that my middle terms, we're going to cancel each other out. Negative 8i plus 8i is 0. And then I think you should also see that we have an I squared term here. Take off the I squared, change the sign, we get plus 4. 16 plus 4 is 20. Unusual answer, isn't it? We multiply two complex numbers and we get a real number answer. I'm pointing this one out because it's what you're going to see when we start rationalizing imaginary denominators in the next video. I also want to point out to you that this is actually a difference of squares problem. And we know that when you do the difference of squares, you get a squared minus b squared, don't you? Well, we could do that here too. A is 4. 4 squared is 16 minus my second term squared. 2i squared is 4i squared. This becomes plus 4 because it's an I squared, 20. It really doesn't matter whether you do this by FOILing or difference of squares. All the difference of squares saves you is a little bit of time in ignoring those middle two terms that cancel each other out. But that's what we've got to say about multiplying complex numbers. Next up, rationalizing or dividing complex numbers. Thanks.